factor by grouping is when you have 4 terms. And when you have 4 terms, then there'll be 2 sets of pairs that you can actually pull terms out of. For example, if you look at this one, you see there are 4 terms. You can't pull anything out of all 4. That would be the first step. The second step would be you look and see what the coefficients are of the terms, and you're going to see the coefficients are 1 and 3 and 9 and 27. But if you're to pull out a 9 out of this one, you're going to see that these coefficients are going to be a 1 and 3 as well. Or you can think of these as ratios. 1 over 3 is the same as 9 over 27. But you could do it this way as well. 1 over 9 is equal to 3 over 27. So you could group the first and the third, or you could group the first and the second. It doesn't matter which ones you group. I like to look at the coefficients and just make sure they match up before I go ahead and do it. But by looking at this, and this doesn't happen every time, the ratios have to be the same in order to group. But you're basically just factoring out an x squared out of the first two, and you're factoring out a 9 of the second two, and you're going to see that both of these have the same thing, and it's like common terms here. So some students will wonder why the second step, this step right here, is equal to that. How can you say that x squared plus 9 is times x plus 3 is equal to what's above it? The reason for that is you're simply combining like terms. For example, if I had a 5y plus a 7y, and the question is combine these two sets, these two terms, you're going to see that since they're the same, you can combine them. So what you're really doing is you're taking 5 plus 7 times y, and then you're just adding those together. Now, you're not going to write down that second step because you can add 5 plus 7. But if you couldn't add 5 plus 7, that's what you're doing in this step right here. You're saying x squared plus 9 of the x plus 3s, right? X squared plus 9 times x plus 3. You're combining the like terms right here, but I can't add those terms together, so I leave it just the way it is. It's like that, but you're stopping at that point. I wanted to show you one other part where you have this negative sign, and that can create some problems. So again, you see 1/4 and 1/4, so it'll probably factor by grouping, taking out the greatest common factor. When I take out a -9, you could do plus -9, or you could just do -9. This becomes x plus 4. Again, the easiest thing to do is go in reverse and make sure that what's up above it is what's supposed to be. And then since they're both times x plus 4, you can take x squared minus 9 times x plus 4. And then this x squared minus 9 can get broken down into one more set of factors because it's a difference of squares. And so then you would stop right there. Okay, so that's all I wanted to do on factoring by grouping, just a different way to factor. The key, again, having 4 terms. And then what I want to do is look at the logs, and I'm going to talk a little bit about the purpose of logs and where they came from. In the past, for the trig units, we started with something basic like y equals sine of x. And then on our graphing unit, we said, well, you know what? Instead of y equals sine x, I can also graph the inverse of this one. And the reason why I'm talking about inverses is because the log is an inverse of an exponential. So we'll start talking about inverses with trig and then just go to the inverse of this other one. So when I did the inverse of this, really what I did was I switched the x and y around. So this became x equals sine of y, right? This is the inverse. They are not equal, they are inverses. And then we said, instead of writing it as x equals sine of y, I can write it as a different way. I'm going to create this sine inverse of x, which is equal to y. In other words, these two right here are equal. So these are inverses. These two are equal. It's just I created a sine inverse to write it where it's equal to y. But really what I'm doing is switching the x and y. The same exact thing is true for exponents and logs. So the common exponent is, for example, where you have a base of an exponent is equal to some number. And then what I want to do is just switch those around. So when I switch them around, you're going to have the base of a number is equal to an exponent. I'm just putting these in terms of words instead of numbers, and we'll do number examples later. But I'm switching the two variables, assuming the base is the same number, right? And when I do that, this becomes the inverse. And there's a different way of writing an inverse, and that is by using logs. All right? Instead of writing this, I can rewrite that as the log base of a number is equal to an exponent. I'm creating this log function so I can set it equal to the exponent. Instead of having my x and y switched, like I did here, I can create a log function and set it equal to y. And you'll see that in examples. But that's why we have a log function, is because I can write this in terms of y, write this one right here. Now, why do we use log functions? We use log functions because I can put numbers that are very large into smaller numbers and make it into a scale, like from 0 to 10, like Richter scales or pH levels of blood. They're in scales of reduced numbers, so it's taking very large numbers and reducing them down into a smaller number, which is something more understandable. Because logs are exponents, and when you're dealing with exponents, it's a smaller number. Okay, that's what you should think about. Log is an exponent. All right, so back to here, you're going to see that it's just the way that you say it. Y equals log base b of x. That's nothing new. It's something that you've seen before. It's just how you say that. And we went through the log form versus the exponential form. Then what I'm going to do is go ahead and do just a few examples in the book. It'll be more concrete for you, and you'll see how to exchange between one form and the other, and simplify a couple problems, and then we'll get into graphing as well. So if I look at number 7, and I'm on A16, which is the appendix 16 in the back of the book. It's way at the end. Page numbers go into A's. And so when I'm looking at this, it says change the form to log form. So it's 1/2 to the -3rd is equal to 8. And you want to change it to log form. How do you change that to log form? Well, again, you remember the base goes with the base of the log, the exponent is what it equals, and then the number is what the log is of the number. So I'm just going to first write down the log. Base is the same exact thing, base and base. The number is 8, and the exponent is what the log equals, -3. oftentimes in logs, you'll think about it. 1/2 to the negative third is equal to 8. And that's how you're thinking. 1/2 to what exponent equals 8? 1/2 to the negative third is equal to 8. One reminder on negative exponents: to change the negative exponent into positive, you make the reciprocal of what the number is. Let's take a look at changing it into exponential form. So just doing the reverse of that. If we look at 16, it says log base 3 of 1/81 is equal to a negative 4. Again, simply changing forms. It's not solving for anything. It's just changing from one form to the other. So again, start with the base, like you did here, log, and then the base. So base 3 to the exponent of negative 4 is equal to the number 1/81. Switching them around kind of makes sense that you're taking the 1/81 and moving it here, and this as the exponent, because you're making inverses. Then let's take a look at 18. 18 says solve for x. So now we have not just writing a form, but actually solving for x. Log base 2 of x equals 1/4. Log form is hard to work with. It's kind of like in exponents, you don't like to deal with radicals or square roots. You want to write it in exponential form. Same thing goes for here. You want to change log form to exponential form, because then you can go ahead and solve it. So again, I want to change it around so it becomes 2, the base, to the negative 4th is equal to x. You have that negative exponent, so that becomes 1/2 to the positive 4th equals x, and that's 1/16 is equal to x. Once you change that around, it becomes pretty obvious in terms of what x equals. Let's go ahead and look at number 22. 22 says solve for x as well. So it becomes log base x of 16 is equal to 4. Again, change it to exponential form and then solve. So it becomes x to the 4th is equal to 16. Some of you can see that x has got equal to, but an easy way to do this, if it wasn't so obvious, would be you'd write x to the 4th, and then you'd try to figure out what number is it to the 4th power. So if the exponents are the same, the bases have to be the same. If the bases are the same, the exponents have to be the same. So your question really is, what number times itself 4 times is equal to 16? That answer is going to be 2. So x is equal to 2, because you know that has got to be a 2. Let's go ahead and look at graphing. So the graphing part of this is we're going to graph both the exponential, and then we're going to go ahead and graph the log. So we're going to graph both inverses. How do you do it? Y equals 2 to the power of x. Well, we're going to make a big table for both of them and see how we go from there. So this is going to be x and 2 to the x. And then we'll go ahead and plot the first one, and then we'll do the other one in red. All right. By putting in x, again, I want to pick easy x's. So if I use -2, this is going to be 2 to the -2, or 1/4. 0, 2 to the 0, which is always going to be equal to 1. One gives you 2, and 2 gives you 4. So that's just a few points, and then when I graph them, it's going to look like this. And you can see it's an exponential, and when it's an exponential, it's going to come like this, where it's rising, and then eventually it's going to go toward the y equals 0. And when it's toward y equals 0, it's not going to actually hit 0, because no matter what you put in for x, if it's positive or negative, you're going to have a positive fraction here, or a positive number. So because it's positive, it'll never get to 0. That means it's going to keep getting closer to 0, but never touching it. If you had a negative 1 billion, it would be 1 over 2 to the 1 billion, which is a very small number, which means it's going to be coming out this way. All right, so that's what that looks like. Now, if we change that around, and we now want to write, for example, 2 to the y and put in our x's. I can start here with my y value. If my y, for example, is 0, 2 to the 0 is 1, look what happens. This is 1, 0 now instead of 0, 1. If I look at y being negative 2, my x value is going to be 1/4. So there's my negative 2 1/4 is now 1/4 negative 2. If you look at 2, for example, 2 squared is going to be 4, so we now get an x is 4 and a y which is 2 instead of 2, 4. We're switching the x and the y, inverses. So let's go ahead and graph that. So that's going to be 1, 0, 1/4 negative 2, and 2, 4, 4, 2, rather. And as you graph this, you're going to see that that's going to be moving in that direction. Well, how does that work? It works by actually reflecting about this x equals y line. All inverses have a property that they can reflect about that x equals y line. So what do you have? Instead of that red line being x equals 2 to the y, we now can say that that's a log function, and that's how we're going to label it. So it's going to be, instead of writing it this way, it's the log of x is equal to y. That graph is this graph right here, and these are the points. Okay, this has no y in it. Y equals, so you can't graph it. This does, so that's how you're able to use your calculator. All right, so that's the graphs. Furthermore, a couple more points, and that's it. We're going to go ahead and just look at these identities. These identities are more complicated than what they appear more complicated than what they are. I think if you think about them in terms of inverses, it makes a little bit more sense. And the idea is the composite of inverses is equal to x. In other words, the exponential of the log is equal to x. You have an exponential and a log composite together. On this one, you have the log and the exponential mixed together, which is a composite, which is equal to x. So inverses, composites equal to x. Let's go ahead and look at number 29. Now, this, you don't really need to know that to solve problems. This idea is mainly used in proving identities, log identities. So let's go ahead and do 2 more problems. Log base 25 of 125 is equal to what? You're simplifying. So the goal here is not to change forms. It's to say, what does that actually equal? You can change forms, and that's what I would suggest doing to make sense of this. 25, the base, to what exponent equals 125? 25 to what exponent equals 125? By looking at that, it's not so obvious. If you had a 1 here, it's 25. If you had a 2 here, it's 25 squared, which is bigger than 125. So it's somewhere between 1 and 2. But the way, again, to solve this is to raise both of these sides with a base of 5. 25 is the same exact thing as 5 squared. And then that's equal to 25 to the power of what we're trying to find. And then 125, if you were to look at this, 5 comes out of it. That's going to be 25 times. So there are 3 5s. That's 5 to the third power, which means this is 5 to the third power. Now it becomes a lot clearer in terms of what goes in that box. And what goes in that box is going to be 2 times whatever that is equal to 3. So you know that that box is going to be equal to 3 halves. And that gives you a system to use in order to find any exponent like that that has the same bases. You just make an equation and get your answer. Let's take a look at number 38. 38 says you have the log base 5 of the log base 3 of 3. Now it's not the log times the log, it's the log of the log base 3 of 3. So the question is, how do you do this one? Well, you always start with the inside parentheses, work out. So I'm going to start with this. By starting with this, my question is, now it's the same idea as this, 3 to what exponent is equal to 3? And that answer is going to be 1. So some of you don't have to say 3 box equals 3. You can just know 3 to the first is equal to 3. So you now write this is the same thing as 1. And now the question is the same idea. 5 to what exponent equals 1? 5 to the 0 is equal to 1. And now you're done with that problem. Okay. A lot of this is little stuff with logs. Logs can be a little bit confusing because you're just really not sure if you're doing it right or not. But I would say gravitate to the properties or the definitions, and then you can't go wrong. So just keep those in front of you as you go through this. Okay, we're going to have 2 more days on logs, then a review, and then we're going to have a quiz.